Wave equations. This is a video tutorial for advanced placement physics or anybody else who comes across it. But I think I'm going to give you maybe a little bit of a different angle on the wave equations. There's kind of a theme behind this that I want to suggest to you. First, I want you to think in terms of a phenomenon called standing waves. We're not going to talk about standing waves in detail in this tutorial. However, I want it to be in the back of your minds. I want you to think of it as a future goal. This is something I want to understand, and I'm going to understand it partly through wave equations. So, got a little schematic here, kind of like a flow chart that I'll be building for you. But let's take a look at what Turgeon means by standing waves. Here is an interactive, and I apologize if the frame rate makes this look a little choppy. This is a standing wave. There's something special about standing waves. They're very useful to us in the laboratory and in physics problems, and there's a reason why they are so emphasized, and I want you to have that in the back of your mind, and I understand that right now. And through the course of this video, I'm going to be raising just as many questions as I answer, and that's sort of what I'm going for. This could also be called a harmonic, and what I mean by that is it's a particular harmonic. Do anybody want to guess which harmonic I'm showing you? Just take a guess. It's like which one? What number harmonic is this?
3.
It's the third. This is the third harmonic. The first harmonic is also known as the fundamental. Second harmonic, third harmonic, fourth harmonic. We'll get into a lot more detail on that when we get more into standing waves. This is not really a tutorial about standing waves, but standing waves are really important to this. But let's keep this in the back of our minds, as I've said. Standing waves can also be thought of as harmonics. They can also be thought of as resonance. I'm just introducing some vocab, and you'll see that in different contexts, these terms. Harmonics, resonance, standing waves. More to come on that. That's the what. The phenomenon that we can see and we can describe is this phenomenon of standing waves, which raises the question, why? Why do standing waves occur? So sorry if there's any glitchiness in the video there for a second. It looks like it didn't capture this part, so here we go. What we have here is a standing wave. You could also call it a harmonic. Which harmonic, just take a guess, which harmonic do you think you're looking at?
4.
It's the fourth harmonic, okay? It happens to be fourth harmonic, has to do with the number of quote-unquote humps that you see, the number of, people would say, oh, the number of waves that you see. There are peaks and valleys in there, okay? And when we draw it, we'll draw it like that. But we're not going to get into what the standing waves are right now. We're just going to get into, I'm just trying to raise the question. How do these relate to the physics equations? So, standing waves can also be referred to as harmonics, resonance, more on that later. But this, like I said, is related to the what. It also raises the question why. Like, what is causing these standing waves? And I've got different pieces of that picture as to why. Why are standing waves formed? How are they formed? And there are, as far as I'm concerned, 3 pieces to that. There's something called wave interference. And there are 2 equations. There's this really important equation, which I call the wave equation. That's one of the main subjects of this tutorial. There's another equation that is equation of wave velocity. This one's different, though, and it might be a little hard to read here. Let me mess with that a bit. But this one's a little different. I'll give you a little more precision on that. This one is, I call the physical wave equation. That says V equals the square root of ft over this Greek letter P, which is rho, stands for density, but it's a particular kind of density. We're going to get into that. I'll explain all of that. My point is I want you to see right away that there is this distinction between these two different kinds of wave equations. So this informs the what, this informs the what, this informs the what. All of these pieces go into explaining standing waves. Does that make sense so far, at least what I'm... Here's one of the other angles that I think is a little bit unique that I want to present to you. Going back to one of the big questions of the unit, what does wave motion look like? And if we look at waves, we realize that there's two distinct motions occurring within any wave. In those two distinct motions, you can identify points and you can look at what's happening at that point. In fact, you can pick any point. However, if we're tracking the wave itself, we call that a wave velocity. Also known as, what's the term for wave velocity if we're watching this wave travel through space? What's the term for that? You got a wave that is transferring something from one point to another through space. It's translating through space. Propagation. Good. So this is representing the wave propagation. It's one arrow. Then we have the individual particle oscillation, the matter of the wave, not the energy. The matter just kind of goes up, but it also goes down. So we can see that the wave transports energy, but the wave does not transport matter. This is oscillation, this is propagation, also known as wave velocity. We've already been over that. It's a good review. But what I'm really trying to get into now is I want you to see a connection to the wave equation. And the wave equation has a velocity and a frequency. I want you to see when you look at this that this velocity and this frequency relate to this question of what does wave motion look like. This frequency, what does that make you think of? When I say frequency, what part of that previous slide does that make you guys think of? People are making up and down motions. And say it out loud for posterity. Yeah. It's cycles. Frequency is cycles. What about from the previous slide? What does that remind you of? Oscillation, aka vibration. Those terms are synonymous. So this is the frequency, but I want you to picture that's the frequency of an oscillation. The v is the velocity of the wave itself. This new upside down y looking thing, which is the Greek letter lambda, that's the wavelength. One thing that I'm going to emphasize is that this property, this velocity is a property of the medium. This wave velocity is a fixed property of the medium. If you want to change a wave velocity, like you want to change how fast a sound travels, like the snapping of your fingers, you got to change the medium. If I want the hand clap, if I'm a coach and I'm clapping my hands to get the attention of my athletes, what happens if I run toward them while clapping my hands? Do I get the sound to them faster? I don't. I get a little closer to them. Maybe it's a little louder. But the act of moving toward an object or a receiver of sound or any wave, that does have an effect on what is received, but it doesn't make the sound get there any faster, believe it or not. Now, I know some of you are thinking of the Doppler effect, and that's what I'm referring to, but that doesn't make the sound get there any faster. This part's really important. The velocity of a wave is results from properties of the medium. Even in a way you could say light waves are related to properties of space itself. You can write the speed of light in terms of other universal constants. Does anybody know what those universal constants relate to? You would have had to do some, have taken interest in electromagnetic waves to really know. It has to do with the way that space itself can support electric and magnetic fields. And those two constants can be written together in a certain form to produce the speed of light. My point being that that speed of light is a property of the medium, even though light doesn't need a medium. But you sort of could say that the medium for light is space itself. Okay, let's do a really concrete problem. You could pause the video and check this out. I'm just making the point that, oh, actually, I'm going to go back a second here. I just want to show you where this derives from. This is kind of interesting. You could sort of think of this as a kinematic situation where I could say that velocity is distance over time, but the distance is the wavelength, which I can't really do this well in Easy Teach, so I called it an L. That's an Easy Teach L. So it's length divided by time, but the time is the period, a capital T. So this is really just distance over time, but it's length over time. So why does it look like length times frequency? What do we know about capital T and lowercase f? They're inverses. So if I say length, meaning wavelength, divided by the time, that's just like saying the wavelength times the frequency. So that's really where this comes from. You can just think of it as distance over time, but it's a special distance and it's a special time. And here's an example. I'm just going to sort of point at it and say, hey, see how you would use this? Very simple. You just look at, you can take some information about waves and just think about what that means when we say a frequency. What we mean when we say a frequency is we're sort of tracking cycles past an observation point. For your eardrum, that observation point is the eardrum itself. It's receiving waves, a certain number every second, and we interpret that as pitch. For a microphone, does the same thing. The sensors in a camera are picking up frequencies of electromagnetic oscillation. So here's another one which is related to this. I would consider a physical property of a wave. And what we have here is, and I'll explain what each of these pieces means. But this is, I'll try to say this in a lot of different ways, but if you just have a guitar string sitting there, you can say what the wave speed would be. If you just stretch a spring across the room, and you know that someone's about to send a wave, you could say what the speed of that wave would be, the wave propagation speed. It's related to the tension. If you've ever tuned a guitar string, you know this. It's related to the linear density. You'll notice that the thicker strings have a lower frequency. We'll get into the frequency part, but this is just describing how quickly the waves would propagate. Now look at this part. This makes sense because if it's more tense, then each individual particle is more readily able to transfer the oscillation to the next particle. If it's more dense, it's got more inertia, so it's going to tend to vibrate more slowly and therefore propagate more slowly. So right away, you're seeing these two equations and you're thinking they're both velocity equations. One of them is kind of a descriptive kinematic equation, and this one's more of like a physical equation based on the properties. Kind of like you could say period is 1 over frequency, but you could also say that period is 2 pi times the square root of m over k. So here comes another example. I'm going to pause this for a second, prepare the next example. The concepts are there. Pause the video and try plugging in. What you'll see is that I'm essentially just, this requires me to understand linear density, plug into the equation, and I'll get a satisfying answer. Linear density is simply the mass in kilograms divided, a student did this in the past. I had a student go up on the board, so the writing's not great. But it's linear density, so it's the mass divided by the length. And then I can plug in to tension over linear density,